Imagine if the greatest genius in physics, the man who redefined space and time, made a colossal blunder that nearly derailed our understanding of the cosmos. Picture Albert Einstein, scribbling equations in his cluttered office, convinced the universe was eternal and unchanging. To make his math fit that vision, he tacked on a mysterious term, a fudge factor, that he later regretted more than anything. But here's the twist. That mistake might hold the key to the universe's darkest secrets. From accelerating expansion to the fate of everything, today, we're unraveling the biggest mistake in physics, a tale of human error, cosmic discovery, and mind-bending possibilities. We'll dive into the problem that sparked it all, the current state of our knowledge amid groundbreaking data, the wild implications for tomorrow, and a speculative scenario that could redefine existence. By the end, you'll question the very fabric of the universe and feel the urgency to explore more. Stick with me. This journey could spark your own eureka moment. Let's begin with the core problem, the illusion of a static universe and Einstein's desperate fix. Back in the early 20th century, the prevailing view was that the cosmos was infinite, unchanging, a grand eternal stage where stars and galaxies hung in perfect balance. Einstein, fresh off his revolutionary theory of general relativity in 1915, plugged in the numbers and got a shock. His equations predicted a dynamic universe, one that should either expand or collapse under gravity's pull. But that clashed with everything astronomers observed at the time. A seemingly steady night sky. To Einstein, an evolving universe sounded absurd, like a house of cards that shouldn't stand. So, in 1917, he introduced the cosmological constant, a repulsive force baked into space-time itself, counteracting gravity just enough to keep everything stable. It was elegant on paper, but deep down, Einstein hated it. He called it the greatest blunder of my life, after Edwin Hubble's observations in the 1920s revealed galaxies racing away from us, proving the universe was expanding after all. This mistake wasn't just a math error. It stemmed from a deeper flaw in human thinking, assuming we know the answer before testing it. Einstein trusted intuition over evidence, echoing historical pitfalls like dismissing the wave nature of light because it predicted absurd bright spots in shadows. Experiments later proved those spots real, validating waves over particles. Similarly, Einstein's constant was a patch for a worldview that ignored emerging data. But why was this the biggest mistake? It delayed recognition of the Big Bang, the explosive origin of everything, and blinded us to the universe's true dynamism. Imagine if we'd embraced expansion earlier, we might have unlocked cosmic mysteries decades sooner. Yet, this blunder highlights physics' strength. It self-correcting when Hubble's telescope showed redshifts in distant light, signaling recession velocities up to thousands of kilometers per second. The static model crumbled. Einstein scrapped the constant, but the damage was done. It lingered as a symbol of overconfidence. Fast forward to the current state, Einstein's discarded fudge factor is back, reborn as dark energy, powering the universe's accelerating sprint. By the 1990s, astronomers using supernova as cosmic yardsticks noticed something eerie. Far-off explosions were dimmer than expected, meaning the expansion wasn't slowing under gravity, it was speeding up. Data from the Hubble Space Telescope and later the Planck satellite pegged this acceleration starting around 5 billion years ago, with the universe now expanding at about 70 kilometers per second per minute. That's no fluke. Recent James Webb Space Telescope observations of ancient galaxies confirm it, showing structures forming faster than models predicted. Without this repulsive push, dark energy, making up roughly 68% of the cosmos, fits Einstein's constant perfectly, a uniform force woven into empty space, repelling on vast scales. But here's where it gets exciting. Advanced simulations using AI to crunch petabytes of cosmic data revealed dark energy's fingerprints everywhere. Models from supercomputers like those at Argonne National Lab simulate billions of particles, predicting galaxy clusters that match observations only with this constant in play. Without it, simulations collapse into dense clumps, not the web-like structure we see. Skeptics once doubted, citing measurement errors or alternative gravity theories. But breakthroughs like gravitational wave detections from LIGO in 2015 reinforced general relativity's accuracy, leaving dark energy as the prime suspect. Social media buzzes with debates. Posts on X highlight how 2025's Euclid telescope Data narrows dark energy's equation of state to within 5%, edging closer to confirming it's exactly Einstein's lambda. While some experts question if it's truly constant or evolving, recent neutrino experiments suggest it's stable, aligning with Planck's cosmic microwave background maps, showing temperature fluctuations consistent with a lambda-dominated era. This resurgence showcases superiority in modern tools. AI doesn't just analyze, it simulates complex outcomes, forecasting galaxy evolution over eons in hours, outpacing human calculators. Unlike Einstein's era of pen and paper, we pass vast datasets from surveys like DESI, mapping billions of galaxies to trace dark energy's influence. It's not hyped. 2025's findings resolve Hubble tension discrepancies, where local measurements once clashed with cosmic ones, now reconciled at 73 kilometers per second (MPC). Counterarguments persist. Modified gravity theories like MOND explain some anomalies without dark energy, but they falter on large scales, failing to match cosmic microwave patterns. Recent breakthroughs, like detecting dark energy's effects on void growth in the universe's emptiest regions, tip the scales toward lambda. We're not just correcting Einstein's mistake, we're building on it, turning a blunder into bedrock. Now, zoom out to the future implications. If dark energy reigns, the cosmos faces a chilling destiny, but one ripe with opportunity. Projections show expansion accelerating indefinitely, diluting matter until galaxies drift apart, stars wink out, and the universe cools to near absolute zero-hour heat death in trillions of years. But dark energy's strength, parameterized as W approximately equals -1, could vary. If it's phantom energy with W less than -1, it tears atoms asunder in a big rip, shredding reality in mere billions of years. Data leans toward W equals -1, a constant push, but uncertainties evoke urgency. What if subtle shifts, hinted by JWST's early massive galaxies, signal evolving dark energy? This could unify quantum mechanics and gravity, resolving the vacuum energy puzzle where quantum fields predict a constant 120 orders of magnitude too large. Emotionally, it's wondrous. Dark energy powers the vastness, allowing life to emerge. Yet urgent inequality in access to cosmic knowledge could widen, with only advanced civilizations harnessing it. Online forums erupt with fears of isolation, galaxies becoming unreachable as horizons expand faster than light. Yet plausibly, it unifies us. Fusion from dark energy insights could yield unlimited power, as futurists predict, enabling interstellar travel before isolation sets in. Retirement, obsolete in a rejuvenated society. Counterpoints, some claim dark energy is illusionary, from inhomogeneous models, but 2025's BAO measurements from DESI debunk that, showing uniform acceleration. The key, ethical stewardship, steering discovery toward sustainability. Finally, immerse in a speculative scenario. It's 2147, a century after Einstein's blunder echoed anew. Humanity, evolved through AI symbiosis, probes dark energy's veil. Born in 2070, physicist Arya rejects outdated dogmas, leading a team merging quantum computers with gravitational sensors. Society transformed. By 2030, dark energy models predicted resource crises, sparking global unity. By 2045, lambda drives harness repulsion for faster-than-light communication. Minds expanded via neural links. Arya wonders megastructures orbiting black holes, teeming with hybrids exploring quantum realms. Cities float on anti-gravity, problems preempted by simulations. No scarcity abundance from vacuum energy, but Arya senses a void. Hacking archives, 1920s static illusion, 1990s acceleration shock, 2020s AI breakthroughs. A holographic entity, once her mentor, approaches. Embrace the constant. Humanity didn't adapted. Arya hesitates. Loss or evolution. Recalls warnings. Runaway expansion, isolation risks, but hopes. Multiverse portals via dark energy fluctuations. In her final insight, as simulations fail, she smiles. Physics story endures, bolder than ever. What a cosmic odyssey. This blunder ignites our errors fuel progress, but it demands vigilance now. Comment, fear, or embrace dark energy. Would you chase its secrets? Share with debate-loving friends. Subscribe for more paradigm-shifting tales. Together, Let's decode the universe's next chapter. Thanks for joining. See you in the stars.